Here's a polynomial function that we would like to solve or find the roots. And we're going to use the rational zero test. So I'm looking at the factors of the leading coefficient, the factors of the constant, and then looking at all of the variations of the factors on the right over the factors on the left. So I've got plus or minus 1, plus or minus 1/5, plus or minus 2, 2 over 5, and there are all the factors that are possible, or all of the roots that are possible. So we start testing these. I'll just go from left to right. I'll try f of 1, and that'll be 5 minus 9 plus 28 plus 26, which is clearly a non-zero value that is positive. F of negative 1, that's clearly a non-zero value that is negative. So right here, just reflecting back to our use of the intermediate value theorem in the past, we can see that going from positive to negative, there has to be a 0 on the interval between 1 and negative 1. That could be useful. So let's go on to look at f of 1/5. See how that's going to be. 1/5 is going to be 5 over 125 minus 9 over 25 plus 28 over 25 and plus 6. So a quick question would be, does it look like all of the positive values are going to balance out with all of the negative values? And the only negative value I have is this little negative 9/25 here. So this is obviously going to be non-zero and positive. What does that tell us about our intermediate value theorem at this point? I've got a positive value at 1/5. I've got a positive value at 1, and then a negative value at negative 1. So this narrowed it down. Let's continue this. It might be interesting to look at. Is that now with all of these, so I will go in here and include this other value here. Now with all of these, just stop and consider a moment. Can you tell what the interval is where there will be an x-intercept? Okay, so that'll be between negative 1 and 1/5. Because negative 1, f of negative 1 is a negative value, f of 1/5 is a positive value, so there has to be a 0 somewhere in there. Let's go on to try f of negative 1/5. All right, so I'm going to have a negative 5 over 125, and I'll still have minus 9 over 25, and then I'm going to have a minus 28 over 5. I did that incorrectly up above, you may have seen already. So let's go ahead and just fix that. So this should have been a 5, which wouldn't change our analysis at all. And then continuing with f of negative 1/5, I'm going to go plus 6. Now let's look at that. I've got these this positive value 6, and then will these balance it out? So I've got that value, and that value. Could that all add up to 6? In which case it would be, negative 6. Yeah, that looks like that could be a possibility. So here are all the negative values with the common denominator of 125, and this actually does come out to 0. So we found a root. All right, so we're going to carry that root forward. So we've got this f of negative 1/5 is equal to 0. Now that means that we know that x plus 1/5 is a factor of this polynomial. And I'm trying to do 1/5 here. And that fact that negative 1/5 means x plus 1/5 is a factor, let's just comment on that. That is using the linear factor theorem. So if negative 1/5 is a root, as we know, if negative 1/5 is a root, then x minus negative 1/5 is a factor. So there's just a little terminology we want to be familiar with. And of course we know now that we can find the other factors by division. So I'm going to set up the synthetic division here, and then we will carry that out. And we know at this point, and you should also know at this point, that if I'm dividing f of x cubed, or if I'm dividing f of x equals 5x cubed, so if I've got 5x cubed and I'm dividing by x, I'm going to depress this to x squared. So I know that the new factor is going to be x squared, and that is helpful to us because we can always solve x squared, if not by factoring, then by the quadratic formula. So let's do this division. Negative 1/5 times 5 is negative 1. And I'll add negative 9 plus negative 1 to get negative 10. Negative 1/5 times negative 10 is 2. And I will add 28 plus 2 to get 30. And negative 1/5 times 3 is negative 6. And there's our remainder of 0 as expected. So this factor is 5x squared minus 10x plus 30. And let's carry that forward. So to finish solving this, we are going to want to factor the second factor. Now we see there's a 5 I'm going to factor out from this right here. So here we've got this all factored out, including I factored the 5 from the 5x squared minus 10x plus 30, and that leaves us with this factor where we can find the additional roots. Now looking at that, we can see that we're not going to be able to factor it, so we're going to use the quadratic formula. So I'm going to say that I've got negative b plus or minus the square root of b squared minus 4ac over 2a. And that simplifies to this, which simplifies to this. Maybe I didn't need to rush through that, but yeah, there's going to be a 4, a 2 rad 5. Now that 2, there's going to be a 2 that cancels there. I want to be careful about rushing through that. So this 2 is going to cancel, right? Because I'm going to have rad 4 times rad 5, which is 2 rad 5, and then that'll cancel with this 2. Okay, so those are the roots. Now let's finish. So the answer to the question might be, depending on how it's phrased, this might be the answer to the question. A solution set, and these are my solutions. So let's talk about that. Talk about this solution just for a moment. Given the instructions, given f of x, find the roots with f of x equal to this, and I went to the factored form. So that wasn't what was originally given, but we were able to factor to that and then continue from there and solve and find these roots. So a few things about this. One is that what if you were given these, and we said find f of x. So that's another wording that could be used. It could be given roots, and then you would be given the roots, find f of x. And then remember this linear factorization theorem that I talked about back here, this linear factorization theorem here. So what that says is that if you're given the roots, you've got the factors. And if you have the factors, you can find the polynomial. So we would just be going in reverse. And let's just look at what that looks like. If I were to say f of x is equal to x, and then I go minus a negative 1/5, which is x plus 1/5. So we already did that, something like that before. And then look at these other roots. So it's going to be x minus, and then put parentheses, 1 plus rad 5I, and then times x minus 1 minus rad 5I. So do you see how that works? And then we would probably, yes, need to multiply this out and simplify it. And that would be a little bit, take a few steps, but shouldn't be anything that's too difficult. And then another thing to notice, one last thing to notice here, is that, look, if you, and I would rather have the original function, so I'm going to take this and replace it with the original function. Here's the original function. Given this function, if these coefficients are all real, and that's always going to be the case for us. I mean, our coefficients are probably always going to be all integers. But even if they're not integers, if they're real, so I could have a radical coefficient here. But if these are all real, then these roots here, I will always have, if I have imaginary roots, I will have conjugate imaginary roots. So, for example, like the general case would be, if I have a plus bi, then I would also have a minus bi. And that is called the conjugate root theorem. Which is, look, all you need to remember is that you can't have a single imaginary root in any of the polynomials that we're going to be examining. And that is it for this topic.